By these transformations, it's possible to write any linear program in a variety of forms. Two forms, however, tend to be the most convenient and widely used. First is what we'll call the symmetric form. We'll see why it gets that name when we consider duality. And second is the standard form. The key difference between the two is that we have changed the inequality for an equality. To better understand the relationship between these two forms, I'm going to write the standard form in terms of the symmetric form. To convert the m inequalities to equalities, we introduce m slack variables, xn plus 1 through xn plus m. And of course this means that we need to augment our matrix A as well, so that the slack variables can do their job. And C also needs to be augmented so that we can multiply it with the new x without changing the value of the objective function. It's interesting to think about the differences between these two forms geometrically as well. In the symmetric case, we're optimizing over a polytope in n dimensions. In the standard form, however, these equality constraints here define something called a flat, which is rather like a subspace, only it's away from the origin. And then we're intersecting that with the cone defined by the positive coordinate axes. And of course, we're in a higher dimension. Note that we expect an optimum for the symmetric problem to be at one of the vertices of the polytope. That is to say, of these m plus n constraints here, n must hold with equality, or be tight in the common parlance. Some might come from A, some might come from the non-negativity constraints, but there will always be n of them. Over here in standard form, the notion of whether the constraints of A are tight or not is captured by the slack variables that we introduced. A slack variable is 0 if and only if the corresponding constraint is tight. Thus, at least n of the variables will be 0 when we're at a vertex of the original polytope. In fact, if I tell you which n variables are 0, and the ones that are non-zero correspond to a linearly independent set of constraints, then you can construct the rest of the variables based on the equality constraints. We'll see this when we talk about basic solutions. Now so far, I've kept on using the number of variables n and the number of constraints m from the symmetric form, even as we talk about the standard form. In general, however, when discussing the standard form, we redefine n to be the old n plus m. So don't get confused about that. One other thing to note about this equality form is that we can assume that A is full rank, or has rank m, where m is the number of rows. That is to say, the rows should be linearly independent. If the rows aren't linearly independent, then there are two possibilities. One is that the constraints are inconsistent, meaning that there is no solution. The other possibility is that the constraints are redundant, meaning that some of them can be eliminated. So from now on, we'll just assume that A has full rank.